So, hi everyone. So, I decided to make a YouTube playlist or series about simple harmonic motion and vibrational wave. So, this course will discuss vibration and waves. So, it goes through everything of vibration of waves and the topics of vibration. For me, vibration and wave are just application of differential equations, i.e. equations that involve derivative. So what you expect to know in this course, first thing, you have to know some calculus. That's 100%. You should know about calculus. Two, you should know some basic mechanics. So you must know calculus, basic mechanics, and third thing, you must have a good understanding of differential equation, and most importantly, you must love, with a heart in front of it, physics. So if you have those four things, we are ready to start simple harmonic motion. It's basically, we're ready to start vibration and waves. In this series, I will just go through it as informal as possible. So I don't want to go that much into a lecture style lecture style. I want to do just my style of teaching, which I love teaching, so I'm gonna do it using my style of teaching. So those four stuff you have to know a basic understanding of them. Let's start with something called simple harmonic motion. Why do we start about stuff with simple harmonic motion? Because we want vibration. We want to have stuff that goes up and down and just move something that have some periodic properties. So the basic stuff that we can think about or can understand about is simple harmonic motion. Imagine you have a cube of mass m and you attach to it some spring. And right now it's in the equilibrium position. It means that F net is equal to 0. There will be some forces acting on the block like mg and the tension. But at this position, at this moment, it's mg and normal force. But at this moment, there won't be any tension. So T is equal to 0. Then, and this is the equilibrium position. If we call the equilibrium position as x equal to 0. Then from here we just stretched the cube a little bit. We stretch it by a distance of x. We know from Hawkes, so we stretch it from a distance of x. Why not there is a force? Since we essentially stretch, imagine you have a spring and you just draw and you pull it this way. The spring will throw itself that way. So if you put it this way, it will throw itself to go that way. It's like if you're in the gym machine or something, you put it this way, it will go back that way. That's like in the past, some people used to train using strings. That's the same thing as resistance band. So if someone trained with resistance band, right now you're gonna use physics in sport. If someone trained in a resistance band and he pushed it this way, he gonna feel that the resistance band wanna go back to its normal position. You're going to feel some force from the resistance band. Same thing once you do a biceps curl using a resistance band. If you lift it up, you need to apply force, because there will be some force from the there will be some restoring force that's proportional to the displacement you made. Just like the more displacement, the harder it becomes. So this thing is followed by Hooke's law. Hooke's law say that the force is proportional to the displacement with a negative sign, which means the force will act in the direction opposite to the displacement. We can call it a restoring force because it want to restore the system. So if the object is over here, the force will be acting that direction. So this is the tension, and it want to restore the object back to its equilibrium position. But if we compressed the spring, the compression will be the displacement will be a negative displacement, so it will go into the negative x direction. You can kind of make it an arrow. That's kind of vector from the origin which is the origin to be in the equilibrium position to the final position, and then there's the arrow, and the force arrow will be in the opposite direction, which means the force want to restore the system back into the equilibrium position. So that's so far. That's why the restoring force will be equal to the negative of that thing. Why we want to call it a restoring force? Because if it's in that way, the force will be in direction of the equilibrium position, which means it will restore it. So back into the proportionality, we can say that the force is equal to negative kx. If k is the constant of proportionality, we call it, some books call it negative s k, which I like the s because s is the stiffness. So if you have, like, imagine we have resistance in band that's really hard, you need to apply more force into it to increase the x. And x, of course, depends on some properties, but we're not gonna go into it. It depends on three things quick mention: area, length of the spring. The last thing, it also depends in the material in which the spring was made from. So this is the restoring force. So far we found the equation for the restoring force, and let's continue. That's the F net in the system. There's the weight of the body, and here there's the Fn, and here there's the restoring force, will be equal to ma. And what's a? A is the second derivative of position with respect to time. So we can say it's mx dot dot, which is the second derivative of position with respect to time. So we kind of found a differential equation here. We call negative kx, and like these things, two things are just the same thing. Like in other books, some books called k as the spring constant, another book called the stiffness as the constant, equal to second derivative of time. We can actually say the second derivative is equal to negative k divided by mx. So what does this thing mathematically mean? Mathematically mean the position, we want to find a function whose second derivative is equal to the function itself time negative some constant, which is k divided by x. We can call this constant as negative omega squared x. This may not make sense right now why we call it omega, but we're gonna see why we call it omega for now. So we reach out into a differential equation in time, which is equal to negative k divided by mx. So there's a differential equation with respect to time. From that, what should we be doing with this differential equation? What's the solution? We can think about this. Let's figure out, try to come up with a solution. Okay, so let's try to come up with a solution. Let's have a think about it. The solution of this thing, this solution describes a physical system that oscillates within time. So if you have the spring, you're going to pull it over there. You're going to pull it over there, you're going to do some work. Then the spring, once it goes back into the equilibrium position, because you did some work and imagine that there is no friction, because you pull it, it used to have some energy. In this position, it must have energy, otherwise the energy has been lost, or energy has been converted, like has been lost. But the system does not have any friction force or non-conservative force. There must be some kind of energy, and there's no potential energy because that's the equilibrium position. That's the definition. That's the equilibrium position, and we define the potential energy here to be equal to 0. So which other form that the spring can have? It must have some kinetic energy. So in this position, it must have some kinetic energy, and it's going to go this way. So it will have some velocity going that way. Why is it going to go that way? Because just think about it. The spring was here, and it was gaining kinetic energy because the potential energy was decreasing, so it was gaining kinetic energy. Once it goes here, it must continue that way. So the velocity will be this way. You can also see it experimentally. Then it goes back to the compression, maximum amplitude. And we're going to find out that those two amplitude, this thing, we call it the amplitude. And this thing, if we call it the amplitude, x2, we're going to find that magnitude of x1 is equal to magnitude of x2, which can call the magnitude of x2 as the amplitude. But that's from the differential equation that we can find out. So once it's here, the force will be acting this way. So it will be accelerating that way. And then it will go back into its equilibrium position. After that, it also will continue to move that way. So one way to think about why the velocity must be this way, that's from the kinetic potential energy. Another way is that there's always a force acting in this direction. So there is always a force that is acting in that direction, which means and here the velocity is equal to 0. Since the direction of force won't change, so we're expecting the block to gain velocity in some ratio, in some ratio. We don't know what's the ratio for now, but we know that it's going to gain some velocity. That this reaches maximum velocity because the force will change. The force will change, and it will then it will decrease. Then it reaches the maximum amplitude. Then it goes that way. So it's kind of having a periodic motion. That's how we're going to figure out the function. We want the function that has a periodic, which means the period can be constant and it cannot be. Sometimes it can be constant or it cannot be constant. We don't know for sure, but let's figure out a reasonable solution. A reasonable solution is x is equal to sine of omega t. That's one reasonable solution. That's one reasonable solution. Another reasonable solution is x equal to a sine of omega t, which makes more sense because as we saw in the amplitude, like we want the function which makes more sense. We're going to find out why it makes more sense. So there is another possible solution. Or can be plus a 2 cosine of omega t, right? Because that's kind of, so it can be sine and it can be a sine of omega t. because once you differentiate it, just nothing can happen to this one. So you're going to differentiate that thing, and this is a2 cosine of omega t. And right now we're going to know why omega makes more sense, because what the value of omega should we have? The value of omega to be this thing, we want omega to equal to a square root of k divided by m. So let's differentiate it twice, and I will try to make it in my head. So if we differentiate it twice, this will become, sine will become cosine. So, sorry, sine will become sine, so it will become sine omega squared omega t plus omega squared will be not minus cosine of omega t, and let's take the minus as a common factor. Let's take the cosine as a common factor. So, and this thing is the functions, we call it x. So this should be equal to negative omega squared. And that thing is the second derivative, so second derivative. So equal to negative omega squared. And omega, we call omega as equal to square root of k divided by m. So this thing will be equal to negative k divided by m x, which did satisfy the differential equation. So this thing is a solution. And if you ask a mathematician, he's gonna tell you, or she's gonna tell you, that this is the most general solution for this differential equation. So this is the more general, it's not a solution. This is the more general solution for the differential equation. Okay, so how can we write that thing? We can find that here there is a sine of omega t, and here there's a cosine of omega t, and here there's a1, and here there's a2. So we can write as x as equal to sine omega t plus phi, where some a, we call this thing is the overall amplitude, because this is a cosine and sine, and they will interfere with each other. They will have the same time period. However, once they're going to interfere with each other, they're going to have the overall sine and cosine will have a different amplitude. So well, a1 is equal to a1 is equal to a cosine of phi, and a2 is equal to a sine of phi. And if we plug this thing back, and we find that we're going to find that this expression is equivalent to this expression. So the overall thing is that this, we found the general solution for the differential equation. We started by guessing a solution, then we differentiated again, checking if that's correct or not. We found that's actually correct solution. So we stick with it. We try to simplify it. We simplified it by this thing, and this is the overall solution. What does that mean? A mean amplitude. Wow! A is amplitude, like magic. A is amplitude. Nothing like really strange here. I hope. And omega t. What is omega t? This is a sine function. We know that the period of the sine function is equal to what? It's equal to 2 pi divided by frequency. So it's 2 pi divided by omega. I hope. Oh, there's another way to shake that in. So once t is equal to time period. Okay? Once t is equal to time period, once t is equal to the time period, the ratio should be equal to 2 pi. So omega times t is equal to 2 pi, because that's the period of the sine function. The period of sine function we want is the period of simple sine function is when x is equal to 2 pi. If we let x be this thing, we let x equal to this thing, so omega, and which x we are actually talking about x when it's equal to t, when it's equal to the time period. So omega t is equal to 2 pi of t is equal to 2 pi divided by omega. So that's the period of the simple harmonic thing. So that's when it goes there and come back to the original position. So if we start this thing to be here, so if we start the timer to be here, and it already has this, it already be moving to the right, it will reach some, this is t is equal to 0, then it will reach some position here, the maximum position. Then after that, it will return. Then finally, it will go return here. Then reach some amplitude. Then finally, so this is picture at time. First picture, second picture, third picture, fourth picture, and here's x is equal to 0. And the fifth and the last picture will be fifth and the last picture will be equal. Fifth and the last picture will be the string in this position. And once the string is back in this position, we say that the spring has passed at the time t is equal to time period. Why this thing we don't say here's the time period? Because we want the configuration of the system. To time period means, and period in physics mean the configuration of the system. We want it to go back into the original position. The configuration of this system is not same as the configuration of the system in the first picture, because the system was moving. If we say the system is the clock, then the clock was moving to the right. The clock was moving to the right. In this picture, the clock is moving to the left. So the configuration of this system and the configuration of this system is not the same. But the configuration of this system and configuration of that system is the same. Because why the configuration of the system is the same? Because the clock was moving to the right, and in this position the clock is moving to the right, and they ended up in the same position. So that's the time period for the spring thing. So that's the time period. That's once the system goes back into the original configuration of the system. Okay. So that's the description for the motion. We found out this is the description of the motion of the simple harmonic motion, and we found the meaning of everything except this one. What does phi mean? What does phi stand for? So, let's give it a thought. What is the way in which that we can find the phi? Give me the way. So the only way in which we can find kind of how phi can compute is by putting t is equal to 0. So we will get, once we put t is equal to 0, we're going to get x is equal to a sine of phi. Okay, we're kind of getting closer to the meaning of phi. And what is the possible values of phi? Well, the possible value for phi in which the answer is unique. In which the answer is unique. Or like we don't go to the period like 0 and 2 pi. We don't care about those. 0, okay, you're gonna say it's 0, but not. Because 0, 2 pi, 4 pi, 6 pi, they are all the same. There's, even though that's kind of, you can do it if you want to do it because you're going to solve the question, but it does not make any reason why you should put the value of phi to be like the real numbers, the whole real numbers. It doesn't matter. Don't do it. This does not make any sense. But we can instead put phi to lie between 0 and 2 pi, because if it's 2 pi plus 1, then it's the same as 1, and if it's 2 pi plus 0, 0, 0, 0, 0, 1, it's the same thing as 0, 0, 0, 0, 0, 1, so yeah, that's the point. There's no point. So x, phi we say like between 0 and 2 pi. For the sign of phi will lie between -1 and 1, and therefore x will lie between -a and a. So depending on the and this is the initial x, which is the initial position. Okay, so by choosing phi, we can. I'm gonna say somewhere. Okay, I forgot. It kind of get better to put north or something or I just to make a difference between those two x. So x by choosing the reasonable value of phi, we can actually change the position, the initial position. So instead of making the system always start into the equilibrium position where like x equal to 0, we can actually move by choosing the right phi. We can actually make the system goes between -a, this is the negative direction, and to a. So the value, the reason behind phi is they call it the phase change. It's phase. I think it's a phase. It's something about the face. I don't know what they called it. Something about the face. I forgot. Something about the face. So by choosing different value for phi, we can choose a different initial position. So yeah, we can choose different initial position which satisfy the overall thing. So that's the reason behind we choose phi. So phi is just adjusting the initial position, like it's going here, going to there, we don't know, we don't really care, we just gotta start, okay, we don't have to put this time. So it's like if we like for someone gonna come and tell you like, oh, your equation that I wanted the system to start at equal to 0 from here, but you don't have phi, so your overall solution does not include phi. You say this is the general solution, but your solution does not include the possibility that if t equal to 0, you saw something else other than the original position. But if that's the general solution, not include. So we must have phi to include all possible initial positions. That's for the first lecture in simple harmonic motions and vibration in waves.